Today is Friday the 10th of July 2015, and the following video, concluding the hunt for Gill Broussard's planet 7X, was created by my good friend Astronomy Live. Please be sure to credit him for this video. It was not a video created by me. You will find a link in the description area to Astronomy Live's channel and to this video. Thank you for watching.
Hi folks, today I'm going to be doing an analysis of the image data recorded on June 23rd and 28th, hunting for Gill Broussard's planet 7X. So this is a page from Gill's book, page 38, and it shows a couple of important figures which I used to determine his orbital elements. So we're going to go over again briefly how I did that, and then we'll talk about the images that were recorded along that orbit. So on the right side here we have an overhead view of the solar system, and this is clearly from Starry Night. You can tell by some of the symbols that are present on the orbits, which are specific to the Starry Night software. These triangles indicating the nodes, and these little pips indicating the longitude of perihelion. And then we have a wide overhead position showing a lot more of the solar system, as well as the orbits of some of our deep space probes, including Voyager and Pioneer. So basically I used this figure, and here is an expanded version of it, to calculate the longitude of perihelion of his unknown planet relative to the known planets. So we know the longitude perihelion of, say, Venus and Mercury, and we know where their nodes are as well. So you can actually use this image to measure the angle relative to those points and determine the orientation of the orbit. He also gives the orbital period as being 319 years, so you can use that information to directly calculate the semi-major axis of the orbit. He also mentions the inclination relative to the ecliptic being about 0.02 degrees, and the date of perihelion as being February 17th, 2016. So that right there is all the information you need to directly calculate the exact orbital elements of his orbit. So I did that and plugged it back into Starry Night, and here is his first figure here, recreated using that information. And you can see it's a perfect match with his figure from his book. It's also a perfect match with the second figure, the figure above, showing this wide view and these orbits for these probes. And you can see that it also matches the orbits that I have, the orbit I have here for his planet 7X. You can see that it's located near the intersection point of the orbit of Pioneer 11 with the orbit of planet 7X. If you look back on his figure, that's exactly what he shows, and he shows the date here. This actually turns out to be the same date as the orbits down here, and you can tell that based on the positions of the planets in that figure. And again, this is a perfect match with his figures, and we have further confirmation using an image that he sent a friend of mine who asked him where he would have to point his telescope to see it. And using that information, I was able to confirm that I would be covering the right area. So with some persuading, he sent this picture from his copy of Starry Night, showing the coordinates it would be at a particular location, my friend's location, at a particular point in time. So plugging in that same point in time and location, the orbit that I've calculated directly from his figures matches pretty close. I've also calculated an alternative orbit, which is very similar, but differs slightly to match up better to his prediction of a close encounter between the planet and Earth on March 25th or 26th, 2016. And the coordinates he gives are right in between those two positions. So if we search between those two positions, the nominal and what I call the alternate orbit, we will cover his exact coordinates. But we actually covered a lot more than that. We covered all the way back into Sagittarius, where his planet would be if it were still several years out as far as 2021 or beyond. So we've covered all of that, and that spans about 30 degrees of sky. It's pretty expansive. So we're going to take a look at those images now, and I'm also going to show you how far his planet would move between June 23rd and June 28th. So let me go back to June 23rd, and here is an outline. This red outline shows the field of view of the wide field telescope that I used to take the pictures. And if we go up to June 28th, you can see how far the planet's expected position moves. So that's how far the planet would move between the two images, between June 23rd and June 28th, even if it were as far out as 2021. So it would move quite a noticeable amount. It would not be a small shift. It would be a quite significant shift in the image. And we'll take a look now at the images themselves. If it were closer to us, if it were the nominal or alternate position, it would be an even bigger shift. And in fact, I've actually put in pins here for those positions. These are the images that we took. They are astrometrically solved and overlaid back on top of Google Sky here so that we can see where they are on the sky and overlay them on top of each other exactly using the astrometry. So this is the nominal position for June 23rd, and this is where it would be on June 28th. So it would be quite a big jump. And if I go over here to the position for 2021, you can see just how much of the sky we've covered. And even at 2021, it still would make quite a jump between the two image sets. So that gives you an idea of what we're looking for here. And I'm going to turn these pins off, but just briefly, yes, we've covered that orbit over quite a distance, about 30 degrees of sky, all the way from where it's supposed to be according to this book, all the way into where it could potentially be in the future, he says. It could be still several years out, but he thinks it's most likely to arrive in 2016, and there's a smaller chance that it arrives as late as 2021. So we're going to turn these pins off now and just look at the images and compare and see if there's any star that's moving that much. There might be small shifts due to optical distortions. We should see a huge shift if his planet is real. We'll also see these little dots. The red ones really stand out. There's also solid green and solid blue dots. These are hot pixels. They will appear to be moving sometimes, but really that's just due to the different image calibrations that these images were put through. The June 23rd images were 5-minute exposures, and they were calibrated using slightly out-of-date dark frames. The June 28th images were 3-minute exposures calibrated with a fresh single dark frame. So we should see something moving, a large star moving between these two images if indeed his planet is real. We're just going to go image to image and take a look here. Now, I've actually looked at these images quite extensively over the last few days and looked at them up close, and I don't see anything moving. Now, I will include the links to all of these images, the astrometrically solved, calibrated images, in the video description so that you can download them and check for yourself. And you can check my work. You can download the KMZ file, which you can load into Google Sky like this, and overlay the images on top of each other and just use a slider like this. Now, we're not comparing here to the Google Sky Mosaic. We're comparing my images to my images. We're just using Google Sky as a way of opening the images and opening the astrometrically solved images so they're overlaid on top of each other, and just doing this slider to do a blink comparison between the two. So really, we're not using the Google Sky Mosaic because it is full of problems and missing sections which are not present in the original data, where the original data is fine. The original data is the digitized sky survey in this case, which are digitizations of the old Palomar sky plates. And as I've said many, many times before, go to the primary source of the data. Don't use Google Sky as a primary sky survey resource. That's not what it's meant for. Finding problems in Google Sky doesn't actually tell you anything, because Google Sky itself is the source of many of those problems. You can also see a little bit of image shift here with all these stars on the left, because those stars are at the edge of the field of view, and at the edges of the field of view you do get a little bit of optical distortion. But we're looking here again for big jumps between positions, not small jumps. That's the beauty of using images that are separated by almost a week of time, even though the planet could potentially be still quite far away. Earth's orbit carries it along and provides parallax, which allows us to see objects in the solar system, even objects still quite a ways away, and see that they're actually moving due to the parallax relative to the background stars. Now again, I've looked in detail at these images already. You can see little dots like this. This is another hot pixel. It appears to vanish, but it's not really moving. It's just a hot pixel. It's not forming a point spread function. Due to the atmosphere and the way the optics are working, stars form what we call point spread functions. They're not infinitely small points. I mean, they aren't individual pixels. They actually take up multiple pixels, even if they're very, very faint. The light is spread out over a certain area. And so you can tell right away the difference between a hot pixel and a real light source, a real star, by the fact that the real stars form little spots, little blurry areas, little point spread functions. So that's the quick and easy way to tell the difference. And these images go much deeper than they need to. According to Gill, the planet's current apparent magnitude is about 5.8, which is naked eye magnitude. Now, you would have to be under very dark skies to see it by naked eye. But this telescope is taking pictures much deeper than naked eye limits. These images go down to about magnitude 14. Now, there were no significant asteroids, no bright asteroids present in the field of view at the time, so you won't see any asteroids moving here. But planet, yeah, you would see it. And particularly Gill's claimed planet. Even if it were years away, you can actually solve for the absolute magnitude, since he tells you in his book. Let me just show you real quick. He shows this chart down here on the bottom corner of page 39, and at each start of each month he shows an apparent magnitude for it. And by now it's already crossed 6.5. We're into July now. It's at about 5.8. It was somewhere between 5.8 and 6 when these images were taken. And that's much brighter than the limiting magnitude of the images themselves. And as I said, if you solve for the absolute magnitude and you plot what its apparent magnitude should have been, even if it were several years away, it would still be about magnitude 12, which is just 2 magnitudes brighter than the limit of these images, so it would be detected. Additionally, these images were taken in infrared light, so even if it were somehow magically only visible in infrared light and not reflecting any light from the sun at all, it would still be detected here. But we're not seeing anything here. Nothing that's moving anyway. Again, I will include links to all 42 images in the video description, the astrometrically solved calibrated versions, so that you can download them. The KMZ files will allow you to open them in Google Sky like this. The WCS embedded FITS files, which are called new-FITS in the links I'm going to give, those will open in professional astronomy software. This is just a quick and easy way of doing it. And really all we're trying to do here is blink compare between the images, so this is all we need. Plus, most people already have Google Sky, so it's kind of nice to do it for this kind of video, just so that people can see how it's done with software they already probably have on their computer. Yeah, some of the hot pixels look like they're moving, but they're just hot pixels. In some cases, they are generated by cosmic rays, so they won't appear on every image. They'll be in single images because the camera is sensitive enough to pick that up. The key is that they don't form point spread functions like stars. So that's it. We've searched that entire area of sky, that entire area of space, and there is nothing there. Gill's planet just does not exist. Sorry to tell you. Thanks for watching. Clear skies, folks.
Hello YouTube, this is Dazza the cameraman. Today is Friday the 10th of July 2015, and the following video, concluding the hunt for Gill Broussard's Planet 7X, was created by my good friend Astronomy Live. Please be sure to credit him for this video. It was not a video created by me. You will find a link in the description area to Astronomy Live's channel and to this video. Thank you for watching.
Hi folks, today I'm going to be doing an analysis of the image data recorded on June 23rd and 28th, hunting for Gill Broussard's Planet 7X. So this is a page from Gill's book, page 38, and it shows a couple of important figures which I used to determine his orbital elements. So we're going to go over again briefly how I did that, and then we'll talk about the images that were recorded along that orbit. So on the right side here we have an overhead view of the solar system, and this is clearly from Starry Night. You can tell by some of the symbols that are present on the orbits, which are specific to the Starry Night software. These triangles indicating the nodes, and these little pips indicating the longitude of perihelion. And then we have a wide overhead position showing a lot more of the solar system, as well as the orbits of some of our deep space probes, including Voyager and Pioneer. So basically I used this figure, and here is an expanded version of it, to calculate the longitude of perihelion of his unknown planet relative to the known planets. So we know the longitude perihelion of, say, Venus and Mercury, and we know where their nodes are as well. So you can actually use this image to measure the angle relative to those points and determine the orientation of the orbit. He also gives the orbital period as being 319 years, so you can use that information to directly calculate the semi-major axis of the orbit. He also mentions the